All right, in this video, let's take a look at review problem 3.1. A point is chosen randomly in space, and it has three coordinates, x, y, and z, and each of these are standard normal random variables. Let r be the distance from the origin, which is square root of x squared plus y squared plus z squared, and ultimately we're going to find the density of r, as well as the expected value of r, and the standard deviation of r. Before getting started on this problem, I just wanted to mention parenthetically, this was actually one of the problems that appeared on my final exam back in the dark ages when I took probability as a college student. Number one, let's show that x squared has the gamma distribution with parameters 1/2 and 1/2. We actually did this one in class, but let's do it again. So let x be normally distributed and have the standard normal distribution between 0 and 1. And let's also let a be equal to x squared, just to call it something. Okay, so let's find the probability that capital A is less than or equal to a. This is a transformation, x squared, of the normal random variable a. And so the way that I will approach this is by looking at the CDF of a and try to figure it out. Okay, so the CDF of a, that's equal to the probability that x squared is less than or equal to a. And that's the same thing as x being between positive square root of a and negative square root of a. So this one is a little bit more complicated than some of the transformations that we've seen in class because x squared is not a one-to-one function. If x squared is less than or equal to a, that means x is between these two things. So the CDF of this function capital A is equal to, well, let's see, if this happens, if x is less than or equal to square root of a, but it is not less than or equal to negative square root of a, that the random variable x is somewhere between these two numbers. And so I take the area to the left of square root of a, take the area to the left of negative square root of a, and subtract, and that's the area between square root of a and negative square root of a. So this is equal to the CDF for the standard normal distribution evaluated at square root of a minus the CDF of a standard normal distribution evaluated at negative square root of a. So that is the CDF of capital A. Therefore, the PDF of this function capital A is equal to, let's take the derivative. So this will be equal to the PDF of a standard normal random variable evaluated at square root of a. Now I'm taking the derivative to go from here to here. And so I need to take the derivative of the inside, so 1/2 a to the minus 1/2. Then same thing here, the derivative of the CDF is the PDF for a standard normal random variable, evaluated at negative square root of a. Then I take the derivative of the inside again, and I get negative 1/2 a to the minus 1/2. Now these two things are the same. If I have minus and minus becomes plus, then this is actually equal to this, and so I get the PDF of a standard normal random variable divided by square root of a. That's my a to the minus 1/2 that I see. Okay, so now I need to evaluate this. To evaluate this, I remind myself that the PDF for a standard normal random variable is equal to 1 over square root of 2 pi e to the minus x squared over 2. That is the PDF for a standard normal random variable. So plugging in, we get that this is equal to 1 over square root of 2 pi times e to the minus, now instead of x squared, it is square root of a squared, so simply a over 2. And then I have this extra square root of a down here on the bottom. So that is the PDF. Now, the issue is I want to show, let's look at the problem again, I want to show that this has the gamma distribution with parameters 1/2 and 1/2. So let's see if I can force this to look like the gamma distribution. This is equal to, let me rewrite this as 1 over square root of pi times 1/2 to the 1/2 times a to the 1/2 minus 1 times e to the minus a over 2. Okay, and so let's remind ourselves again what the CDF for a, or the PDF for a gamma distribution is. The PDF looks like this. F of x is equal to 1 over gamma of r, x times lambda to the r, times x to the r minus 1, or to the lambda minus r minus a half, times e to the minus lambda x. So that is the r, this should be r minus 1 here, not r minus a half. That is the PDF for the gamma distribution, 1 over gamma of r, lambda to the r, x to the r minus 1, e to the minus lambda x. So in my case, I see that this is 1 over gamma of 1/2, so that matches this, where r is equal to 1/2. Then I have 1/2 to the 1/2, so there's my lambda here, and there's my r here. So if that's my lambda, that's my r, so lambda equals 1/2 also. Here I have a to the 1/2 minus 1. So there's my r again. Then I have e to the minus 1/2 times x, or times a in my case. So everything matches up. So my PDF here matches the gamma distribution with parameters 1/2 and 1/2. The only difference is that the variable here is a as opposed to x. Okay, so that establishes that the random variable x squared has a gamma distribution with parameters 1/2 and 1/2. Okay, part 2. Find the density of r squared. Okay, so first off, let's take a look at x squared plus y squared plus z squared. So in class, we showed that if a is gamma with parameters r and lambda, and b is gamma with parameters s and lambda are independent, then a plus b also is gamma distributed with parameters r plus s and lambda. So that's something that we showed in class. So similarly, we have x squared plus y squared plus z squared. This one is gamma with parameters 1/2 and 1/2. Y squared is parameters 1/2 and 1/2. And z squared is parameters 1/2 and 1/2. And so the 1/2s in the first slot add up. So this is going to be parameters with gamma distributed with parameters 1/2 plus 1/2 plus 1/2. But the lambda 1/2 stays the same. So if I take a look at r squared, that is going to have distribution with parameters, gamma distribution with parameters 3/2 and 1/2. Okay, so let G be the PDF of r squared. Then G of t is equal to, now once again let's recall what the distribution is for the gamma distribution. It normally goes f of x is equal to 1 over gamma of r times lambda to the r times x to the r minus 1 times e to the minus lambda x. So in my case, my r is equal to 1/3, my lambda is equal to 1/2, and so this will be 1 over gamma of 3/2 times lambda to the r, so 1/2 to the 3/2, times t to the r minus 1, 3/2 minus 1/2, times e to the minus t over 2. Okay, now let's see if we can simplify this. Gamma of 3/2 by one of my rules for the gamma distribution. Oops, I'm sorry, this has gone off the page. By one of my rules for the gamma distribution, gamma of 3/2 is equal to gamma of 1/2 times gamma of 1/2. And the rule that I used there is that gamma of s plus 1 is equal to s times gamma of s. And so I'm using the rule here with s is equal to 1/2. times 1/2 to the 3/2, that is 1 over 2 square root of 2. Then I have t to the 3/2, so that's t to the 1/2, times e to the minus t over 2. Okay, so let's simplify this. Another rule that I need to remember is that, and I used this before, that gamma of 1/2 is equal to square root of pi. And so using that rule, 2's cancel here, and I end up with 1 over square root of 2 pi. So this 2 cancels this 1/2. Square root of 2 times square root of pi is square root of 2 pi, times t to the 1/2, e to the minus t over 2. And that is the PDF for r squared. So that's part 2. Okay, for part 3, we wish to find the density of r. Now, there's actually a formula for this that I presented in class. Frankly, I don't like using the formula. I prefer using the PDF and the CDF explicitly. So we showed before that g of t was equal to 1 over square root of 2 pi, t to the 1/2, e to the minus t. So let little h and capital H be the PDF and CDF of r. And this right here is the PDF of r squared that we just did. Okay, so again, my preference is to find the CDF explicitly and then differentiate to get the density, the PDF. So h of r is equal to the probability that capital R is less than or equal to little r. That's equal to the probability that capital R squared is less than or equal to r squared. And here is the PDF for r squared, so I'll just simply use it. So that's, well, there's the PDF, so that's g of r squared, where g, capital G, is the CDF. So let's take the derivative and get the PDF. So h of r is equal to the derivative of this, which is the PDF, derivative of the outside, evaluated at r squared, times the derivative of the inside, which is 2r. Plugging in, we get 1 over square root of 2 pi, r squared to the 1/2, times e to the minus r squared, and I forgot the over 2 when I wrote this, I apologize, r squared over 2, times the 2r. And so this simplifies. This is equal to 2 over square root of 2 becomes square root of 2. So 2 over square root of 2 pi becomes square root of 2 over pi. Here I have r times r for r squared. And because r is always positive, and this is a distance from the origin, I don't have to worry about distance from the origin. And next we have e to the minus r squared over 2. And so that is the PDF for the distance r. Let's now continue to figure out the expected value of r. To find the expected value of r, this is going to be a direct computation. The expected value of r is equal to integral from 0 to infinity of r times the PDF, which we just found in the previous part for part 3, square root of 2 pi, r squared e to the minus r squared over 2 dr. And so that's equal to integral from 0 to infinity of square root of 2 pi, r cubed e to the minus r squared over 2 dr. Alright, so for this one there's no shortcuts. We just simply have to integrate by parts and see what comes out. This is equal to integral from 0 to infinity of, let's see, so to break this up, let's write this as r e to the minus r squared over 2 times r squared dr, and I have square root of 2 over pi in front. And so the thing in parentheses is the derivative of negative e to the minus r squared over 2 times r squared dr. And so integrating by parts, we get negative square root of 2 over square root of 2 over pi, r squared e to the minus r squared over 2, evaluated from infinity to 0. Then minus negative becomes plus, integral from 0 to infinity, square root of 2 over pi, e to the minus r squared over 2 times the derivative of r squared, which is 2r dr. Okay, now let's evaluate this part. At infinity, we have infinity times 0, and one of our rules is that exponential decay always beats polynomial growth. So technically I have to use L'Hopital's rule, but if I plug in infinity, I get 0. And if I plug in 0, clearly I get 0 because the r squared term here. All right, now this next bit. Notice I've got r times e to the minus r squared over 2 again. And so that's going to be negative integral from negative 2 square root of 2 over pi times e to the minus r squared over 2, evaluated from infinity to 0. Okay, so I just use that same integral again of r e to the minus r squared over 2, using it a second time down here. All right, so let's plug in. If I plug in infinity, I get e to the minus infinity, so that's 0. So I get the 0 here. That goes away, so 0 minus. If I plug in 0, I get 1 on this exponential, so that becomes negative 2 times square root of 2 over pi. And so I get the expected value of r to be 2 times the square root of 2 over pi. And so that's the expected value of r. Lastly, the question asks us to find the standard deviation of r. Okay, so to find the standard deviation of r, I first must find the expected value of r squared. Now that will be equal to integral from 0 to infinity of r squared times the PDF for r. And so that's equal to integral from 0 to infinity of square root of 2 over pi times r to the 4th e to the minus r squared over 2 dr. And I'll integrate this one by parts just like before. So integral from 0 to infinity, square root of 2 over pi, r to the e to the minus r squared over 2 times r to the 3rd dr. So that is integral from 0 to infinity of square root of 2 over pi times e to the minus r squared over 2 prime times r cubed dr. Then applying integration by parts, we get negative square root of 2 over pi times r cubed e to the minus r squared over 2, evaluated from infinity to 0. Then minus a minus becomes plus, integral from 0 to infinity, square root of 2 over pi e to the minus r squared over 2 times the derivative of r cubed, 3r squared dr. Okay, so this part becomes 0 again, just like before, 0 minus 0. This part I'll integrate by parts a second time. Integral from 0 to infinity, 3 times square root of 2 over pi times r e to the minus r squared over 2 times r dr. So as before, this is integral from 0 to infinity of 3 times the square root of 2 pi, square root of 2 over pi, times negative e to the minus r squared over 2 prime times r dr. So that's equal to 3 times square root of 2 over pi times, well, negative e to the minus, well, let's put the r in front, r e to the minus r squared over 2 from infinity to 0. Then minus a minus becomes plus, integral from 0 to infinity, 3 square root of 2 over pi times e to the minus r squared over 2 dr. All right, now this part over here is simply 0 as before. At infinity, we have exponential decay versus polynomial growth, and so the exponential decay wins. At 0, plug in 0, we get 0 again. So 0 minus 0 on this part. For this part, let's apply a little. We will have used the PDF for the normal distribution. I know that the integral from 0 to infinity of 1 over square root of 2 pi e to the minus x squared over 2 dx is equal to 1/2. Why do I know this? I know this because if I have the PDF of a normal distribution, the area to the right of 0 is 1/2, half the normal curve. So that means if I have simply integral from 0 to infinity of e to the minus x squared over 2 dx, that's equal to square root of 2 pi over 2 all by itself. So the last term here is going to be 3 times square root of 2 over pi. And the only difference is that I have an x instead of an r, but the dummy variable doesn't matter. And I just simply multiply by square root of 2 over pi times 2. And so square root of 2, and 2 cancel. Square root of pi and square root of pi cancel. And so I end up with simply 3. And that is the expected value of r squared. Finally, to get the standard deviation of x, the standard deviation of r is the square root of expected value of r squared minus the expected value of r, whole thing squared. That's equal to the square root of 3 minus the mean, which we found earlier to be 2 times square root of 2 over pi squared. And so this works out to be the square root of 3 minus 8 over pi. And so that is the standard deviation of r. So that's the problem. And if it makes you feel any better, I had to do this on a test for my final exam back in the dark ages when I was in college.